In this lab, we will continue with the traffic data, and we will show some of the new functions that we will use. So from the traffic data, so I'll just show you how the traffic data looks like. So traffic. So the traffic data has 2000 rows and 11 columns, and it looks like this. So what we want to do from the traffic data is we want to subset some of the columns. So we want to from the traffic square bracket comma bracket names of traffic in percentage continuous, and then bracket the list of the columns inside the apostrophe sign. So we want to start comma site ID comma region name comma site reference comma class weight comma site description comma lane number comma flow direction comma traffic count. Close the brackets, and when we check the head of the test JSON, it looks like this. It's the so it's so let's not do head because we want to see the number of rows. So it's 2000 rows by 9 columns, and the columns are these. Okay. So now next, let test JSON equal to traffic. We can also do the same thing using this function, but this function is better because it puts the column in the way we put inside this bracket. So let's test JSON equal to traffic square bracket comma continuous of start comma site ID comma class weight comma flow direction comma traffic count. And when we check the test JSON, let's not do the head because we want to see the number of rows. It looks like this. So there are 1 2 3 4 5 columns, and they are arranged in the way we imported the column. So this is better. So now let's find the object size of test.json. So that's 155,792 bytes. Now let's do lapply of test.json comma class. This will print the class of each of the columns. Let's run that. So start is of type POSIX LT. Site ID is of type integer, class weight is of type character, flow direction is of type integer, traffic count is of type numeric. Then we will do HTML or XML download. So this download we have to do in the we can't do it over here because our studio is not large enough to handle this file, handle the downloading of this file. So we will use our GUI to do this. So that imports. Now we will check the head of traffic daily counts.html, because when we downloaded the file, download.file bracket the web address comma, then we have the name of the file that we want to download has. So that's traffic dash daily dash counts.html. Let's check the head of traffic dash daily dash counts.html. So this is a bash command. This is a shell command. So we will have shell command. So when we do the console, we see the terminal. So click on that, And then here we can type the shell command, head of traffic daily counts dot html, and that prints the head, the first few lines. So we can see that this is printed over here. So it's a class equal to user table. Okay, now let's get back to our work. So HTML, let's load HTML into R. We need to import the library XML2. Then let traffic HTML equal to read underscore HTML of the traffic dash daily counts dot HTML file. So this is the full address we have typed, and then it looks like this. We could build a data frame from that list, but instead let's pull out the elements from the HTML with XPath. A little inspection shows that there is a table for each site with class FTR table, and row 10 of the table is the traffic count. So let count else equal XML underscore find underscore all of traffic HTML, comma, apostrophe sign, and inside that we will have double backslash table, square bracket at class equal FTR table, then backslash TR square bracket, we'll have 10 inside, bracket TD, then square bracket 2. Let's run that, and it prints this. Now let me show you step by step what happens over here. So traffic HTML looks like this. Now we will use XML find all, and let's put the parameter, the backslash double backslash table, then that prints this traffic HTML, but all the data, all the table data is over here. Then let's put at we can see that class equal FTR table. So at class equal apostrophe sign FTR table, close the square bracket. We have this. Now we want the we see that TR is there, and then TD. Then let's go to TR, say 6. Let's see what TR6 gives us. TR6 gives us class weight values, and let's do TR10, and that gives the traffic count. Now we can see that the values are enclosed by TD. So there are 2 pairs of TD to cross to get to the values. So let's do backslash TD and square bracket 2, and that prints this. So that's what this function does. Let count equal has numeric XML underscore text of count else. Now count else, we know that it equals this. So let me show you that. So XML text of count else, and that prints these values, but let's print the numeric part of it. So that's what it gives. So the numeric part of it. So let's run this and we get the numeric. We can repeat that for any number, any other columns we require, and combine the vectors into a data frame. Let site else equal XML underscore find underscore all of traffic HTML, comma, double backslash table, bracket, square bracket, at class equal ftr table, backslash tr3, backslash td2. Printing the site else prints this. Let's look at step by step. So traffic HTML looks like this. XML find all, double apostrophe, double backslash, table, then prints this. Now there is class equal ftr table, so let's put that in square bracket, at class equal ftr table, and that prints this. Now backslash tr3, so let's do the backslash tr3. So that's site ID and the values. So let's do td2 to get the values of the site ID, and it prints this. So we don't have to put at class equal ftr table. Yeah. So site equal has dot numeric of XML text of site elements, and that gives this. So now let class elements equal traffic HTML backslash double backslash table of tr6 td2. Let's do that, and it prints this, the light or heavy, and that is for the class weight. The table, the double backslash table, and the backslash tr and backslash td parts of the code are X paths, that is specify parts of the XML document that we want to extract. The double backslash table X path will find all table elements within the document. The double backslash means that we do not care what the parent of the table element is. The backslash tr backslash td X path will find the attribute of elements. Rather than searching the whole document, this X path is made to search within one of the table elements, which is why it works, because every backslash tr backslash td element is a direct child of a table element. Let class equal xml underscore text of class elements. So the class elements are these surrounded by tds, and we want to extract the text. So that gives this. And let df equal data.frame of site, comma class, comma count. So what is site, what is class, what is count? So site equal the numeric part of this, and we found the class has a numeric the text part of the class items, and we want count. The last element is count, and count is the numeric part of the traffic count data. So running that, so let's insert the R command here, R cell, and let's see what site equals to. Okay, so site is we have to run this, so it gives the numeric part of it. So let's run this site again. Yeah, so that's better. Now we want to see what is class. We want the value part of it. So the text part of it. Let's run that. Let's see what is class again, and it is this. And then let's look at what is count. Yeah, so let's put that into data frame. Let's run that again. We don't want this first row, so let's put the condition bracket at class equal ftr table. Yeah, that's better. So we need to put at class equal ftr table. Then we run this again, and we get light and heavy. So now let's run this, and that gives site values, the class values, and the count values. Note that this HTML source is only 50 sites. There are 50 rows, so there are 50 sites. Dimension of df is 50 rows and 3 columns. Now let's run this. XML underscore find underscore all of traffic HTML, comma, double backslash table, square bracket at class equal ftr backslash tr backslash td, and that gives what does that give? The object ID, the start, the region, and that is for the fish table, and so on. This is for the fish table, and then next object ID will give us for the second table, prints all the table elements. Now if we do XML text, then what do we get? We get this. So all the tables here. Okay. Now XML underscore find underscore all of traffic HTML, comma, double backslash table square bracket at class equal ftr table backslash tr2 backslash td2, and we get this. So if I remove td2, let me see what it gives. These are the values for start date, and when we want to see the values, then we do backslash td2. So td, there is one pair of td and the other pair of td gives the value. So that prints all the dates. Now let tables equal xml underscore find underscore all of traffic html, comma, double backslash table of square bracket at class equal ftr table backslash tr td. So we have already seen that it gives us all the tables. Let date equal xml underscore find underscore all of traffic html, comma, double backslash table at class equal ftr, close the square bracket, backslash tr of 2 backslash dd of 2. That will give the date, but we do for same for site, region, reference, class, description, line, direction, count. The only thing we change is we change the value of the tr. So tr of the array number, the number of pairs of tr that we pass. So tr3, tr4 up to the tr10. So we run that. Now let test html equal data.frame of date equal xml underscore text of date, comma, site equal xml underscore text of site, comma, region equal xml underscore text of region, and so on up to the count equal xml underscore text of count. So let's print that, and it prints this. So each of these columns are named as it says, like date, site, region, reference, class, description, line, and so on. The XML underscore text of date part of the code is extracting a character value from the result of XML underscore find underscore all of open and close bracket. This is necessary because the result of XML underscore find underscore all of open and close bracket is some sort of XML node object, an element or an attribute, not a standard R object like a character value. For example, it is the difference. I want to delete this. Okay, let's do CSV download. So download.file of the web address, comma, and then the name of the file that we want to save into. So traffic-monitoring-sites.csv. We put the extension as CSV. We can't do this over here due to lack of storage space. Let's do this in our GUI. And on checking the console, ls minus L that gives traffic monitoring sites, and we want to see the first few lines of traffic monitoring sites CSV, then it gives this. Okay, so now let's do WC minus L. So WC, what does WC minus L will give? Let's see. WC minus L of the name of the CSV file will give the size of the file in the number of lines in the file, and that is 2043 lines. So let's do ls minus L. So we see we have traffic dash daily dash counts.html and traffic dash daily dash counts.json and traffic monitoring science.csv. The three files, traffic daily counts.json, traffic daily counts.html, and traffic monitoring sites.csv, all contain the same set of data values, just in different formats. In my case, they all contain the different set of data values due to the additional columns we have in the files. So let's do ls minus lh of traffic, then star dot star for all the extensions. So the HTML traffic file is in the, and all these files are of size 190, the HTML file is of size 35K, and JSON file is of size 841K, and traffic monitoring .csv file is of size 379K. So the biggest file is the JSON file, and then the CSV, and then the HTML file. Let's do WC minus L. So the HTML traffic file is 794 number of lines. A JSON file has 28,098 number of lines, and traffic monitoring sites .csv has 2043 number of lines. The files are of different sizes, even though they contain the same data values, because the JSON and HTML format files contain a lot of labels in addition to the data files, whereas the CSV file just contains the data values separated by commas, and the JSON and HTML files both contain a lot of spaces at the start of most lines. But in my case, the CSV file is bigger after JSON because of the additional columns. The different number of lines is also a clue. In the CSV file, each row of data is on a single line, but in the other files, each row of the data occupies several lines, hence the JSON and HTML files are much longer. Let's read the CSV file by passing the command read.csv of we put the address of the full address of the CSV file, and that gives, you can see that the number of columns are different for traffic monitoring sites. Now we're putting a full address of the CSV file because I will show you. when we do get working directory, open and close bracket, then it gives it this is the working directory, but the file is in this directory. That's why we are putting the full address. Now let me pass the command gc of reset equal true. Let's see what this gives. Now this gives we can see that the number of megabytes that has been used by the V cells is 48.8, and the maximum number of megabytes used by V cells is 48.8. Let's do library profmem. Now let P equal profmem of the curved bracket, then the curly braces, traffic CSV equal to read.csv of the address of the CSV file. And when we do total P, that will take the total of the memory being used to read that file. So that is 1,774,672. That is the amount of memory that has been used. Now when we do gc open and close bracket again, when we run that command, we can see that the V cells was before 48.8, now it's 48.8. So they are same, and the maximum megabytes being used for the V cells was 48.8, but now it's 52.1. So it has increased by 3.3 megabytes. The GC function tells us how much memory R is using for our R objects. The V cells used are about the same. We can also see the V cells maximum used has gone up by about 3.3 megabytes. 3.3 megabytes. Let's have a look. Yes, which roughly corresponds to the profmem open and close bracket result. During the creation of the data frame, intermediate results were also created, which used up several times the memory required for the final data frame. Let's pass the command object.size of traffic CSV. So this will give us the size of the traffic CSV file, and that is 586,568 bytes. The total amount of memory allocated during the call to read.csv open and close bracket is roughly 3 times the size of the resulting R object. So it was 1,774,672 memory used when we pass this command through, and now when we do the object size is less. So the total amount of memory allocated during the call to read.csv open and close bracket is roughly 3 times higher the size of the resulting R object. Test traffic CSV. Because read.csv open and close bracket creates a lot of intermediate values when it is creating the final data frame. Let's pass the command lapply of traffic CSV, class. Now this will print the class of each of the columns. So XY is numeric, object ID is integer, SH is character, RS is integer, RP is numeric, site ref is character, lane is character, type is character, percent heavy is numeric, equipment current is character, description is character, region is character, and the accepted days, ADT 5 years ago, AADT 4 years ago, up to 1 year ago, are integers. Site type is character. Let's do head of test JSON. Do we have test JSON? Let's have a look. Yes, we do. So let's run this command. So the head of the test JSON is this file over here, which has 5 columns, and then lapply test JSON class prints all the class types of all the columns. Start is of type POSIX LT, site ID is integer, class weight is character, flow direction is integer, traffic count is numeric, and object.size of test JSON is 155,792. Now let's go to the next one. Head of test HTML. Then we lapply bracket test HTML dot comma class object dot size of test HTML. When we run that, so we see that test HTML has these columns 3, 6, 7, 8, 9. So 9 columns, and these are the classes of each of the column, and we can see that all the columns are of character type, and the object dot size of test HTML is 11,800 bytes. The data that is extracted from XML is always character values until we convert explicitly to something else like numeric values. Now let's pass the command system.time open cleft bracket open curly braces, and we put replicate bracket 100 comma read.csv of the address of the CSV file. So when what this does is that it makes 100 copies of the columns of this file, of this file that we read. So it makes 100 copies, and we want to calculate the system time. So the user time is the time that the CPU is spent running the read.csv call. The elapsed time is the real amount of time that passed. When we are only using a single CPU, the elapsed time will typically be longer than user time, because the computer will sometimes be doing other things besides just running our code. So our elapsed time is a bit more than the user time. Okay, let's do the profiling of the output. Let's import the library profvis. So what profvis does is that it calculates the time it takes for the functions to run. So so profvis open bracket, then open curly braces, library of XML2, let traffic HTML equal read underscore HTML of the HTML file, let test HTML equal function of traffic HTML, and then curly braces. Then we put all the date, site, region, reference, class, description, lane, direction, count equal to XML underscore find underscore all of traffic HTML, comma, and inside the apostrophe sign we will have double backslash table, then square bracket at class equal ftr table backslash tr, and then we will have the numbers of the trs that we cross to find the values of those elements. Then backslash td2 will give us the value. Then we form the data frame by passing the command data.frame of date equal xml underscore text of all these date, site, region, reference, class, description, line, all these attributes that we found. And then close that curly braces for the function, then close the curly braces and close the curved bracket for the profvis. Let's run that. So that creates a separate window. This is separate window, and we can see that 10 milliseconds have been used. Let's this is not very clear in RStudio because of the memory. Let's run this in the GUI. So we are going to copy this and then paste it in the GUI. So our GUI, so paste this here. So we see that when we click on data, then we see 10 milliseconds. And where is this milliseconds used? Okay, so which means that not much time has been used, and the only lots of time that has been used is our professional. So it's over here, this function here, and this is yeah, so none of these has taken a lot of time, but 10 milliseconds has taken for the library, I think. Let's run that again. See, let's run that again. Every time we get a different everything. Data r prof. When we click on that, this is for catching. So in general, not much time has been used over here, only 10 milliseconds. So the code has taken around 10 milliseconds to run. Probably we spent most time on the library line of code. One way to make this code run faster would be to supply XML library. So let's write the code again. The code below shows that let's write the code again by supplying the XML2 library. Let's look at the it doesn't make a difference. So it doesn't make a difference. So by putting the library out, it doesn't make a difference. It takes the same amount of time.